Thank you, sir.
Mr. Pereira! අයියෝ මිස්ටර් පෙරේරා මොකද්ද මේ කළේ?
ෆිල්ම් එක නිසා ගේ පේන්ට් කළා.
To comment this prestigious event, we have our special guest at the entrance. The dignitaries are being welcomed with enriched cultural values, embracing our tradition and norms. Ladies and gentlemen, in a few minutes, we will be commencing a great day in Faculty of Engineering. With an immense joy and excitement, stay tuned for the great start.
Good morning, distinguished guests, esteemed faculty members, researchers, and participants. It's with great pleasure and honor that we welcome you all to the second International Conference on Engineering, ICE 2024, under the sphere of Jaffna University International Research Conference, JUICE 2024. This prestigious event is organized by the Faculty of Engineering, University of Jaffna, in collaboration with the Institute of Engineers, Sri Lanka, Barakin chapter. At this moment, we express our gratitude to our gold sponsor, Silex Renewable Private Limited, and our silver sponsors, Asian Paints, Causeway, and KUS Scaffolding and Concreting.
Today, we come together under the conference theme, Striving for Engineering Solutions with Quality of Service. In this dynamic hybrid setting, we aim to engage in meaningful discussions and innovative solutions that contribute to engineering excellence and sustainability. Without further delay, let's proceed with the agenda for the day.
To officially commence our conference, we will begin with the lighting of the traditional oil lamp. This ritual symbolizes the illumination of knowledge and wisdom, and we are honored to have the dignitaries of this auspicious ceremony. With immense honor and pleasure to light the oil lamp, we cordially invite Professor S. Sri Satgunaraja, the General Chair of ICE 2024 and the Vice Chancellor of the University of Jaffna. Professor A. Adpudaraja, the Chairman, IESL Vadakin Chapter and the Vice Chancellor of University of Vavuniya. Dr. Ganeshwaran, the Dean of the Faculty of Engineering. Dr. T. Kedison, the Dean of the Faculty of Technology. Mr. A. R. Ramesh Kumar, Deputy Registrar, Kilnachi Premises, University of Jaffna. Dr. Janathanan, the Convener, ICE 2024.
Professor Thiruvaran, Editor and Head of the Department of Electronic and Electrical Engineering. Dr. Kadir Gamanathan, Head of the Department of Interdisciplinary Studies. Dr. K. Deesan, Head of the Department of Civil Engineering. Dr. Tarsika Thanikaiselvam, Head of the Department of Mechanical Engineering. Dr. Pradeepa Jayanandan, Head of the Department of Computer Engineering. Engineer N. Sudhakaran, Provincial Director, Irrigation, as a representative from ISL Vadakin chapter. A representative from presenters. Thank you all for joining in this auspicious event. To comment this event with an environment of rhythm, grace, and harmony, along with our cultural values, please put your hand together to invite Ms. Kachanika on the stage to perform a welcome dance.
Thank you, Gajanika, for your wonderful performance. We invite the following dignitaries to the head table, please. The Vice Chancellor, Professor S. Sri Raja, the Chairman, Vadakin Chapter, Professor A. Raja, Dr. A. Ganeshwaran, Dr. B. Janathanan, and Editor, Professor T. Thiruvaran. Now, it's our honor to invite Dr. Ganeshwaran, the Dean of the Faculty of Engineering and Joint General Chair of ICE 2024, to deliver his welcome address.
Professor S. Sri Raja, the Vice Chancellor of the University of Jaffna, Professor A. Arpudaraja, the Chairman of the ISL Vadakin Chapter and the Vice Chancellor of the University of Vavuniya, Deans of the Faculties, keynote speakers, esteemed guests, conference participants, and fellow colleagues. Good morning and welcome to the second International Conference on Engineering ICE 2024, hosted by the Faculty of Engineering at the University of Jaffna in collaboration with the Institution of Engineers Sri Lanka Vadakin Chapter. As one of the satellite conference of Jaffna University International Research Conference, JUICE 2024, ICE 2024 offers a valuable platform for the researchers. This year's conference theme, striving for the engineering solution with quality of service, reflect our commitment to advancing engineering practice. This year's event holds a particular significance as we celebrate the University of Jaffna Golden Jubilee and mark the 10th anniversary of the Faculty of Engineering first student intake. First and foremost, I would like to extend a warm welcome to Professor S. Sri Raja, the Vice Chancellor of the University of Jaffna. We are honored by your presence, support, which greatly enriches our gathering. Next, I would like to warmly welcome Professor A. Arpudaraja, the Chairman of the ISL Vadakin Chapter and Vice Chancellor of the University of Vavuniya. Your involvement in this conference is invaluable. I would also like to extend a heartfelt welcome to the deans of other faculties, members of the council, keynote speakers, heads of the departments, professors, academic staff, deputy registrar of the Kilnochi premises, assistant bursar, and non-academic staff of the University of Jaffna. We are truly grateful for your presence here today. I would also like to extend a heartfelt welcome to our valued sponsors representatives. Your presence here not only demonstrates your commitment to our shared goals, but also enriches the dialogue and connection that would unfold during this event. I apologize sincerely to anyone whose name may have been inadvertently missed. Your contribution, participations are vital to the success of this conference. I appreciate each and every one of you. Finally, I would like to welcome all conference participants. Your engagement is what makes this event meaningful, and I look forward to the inspiring discussion ahead. Thank you.
Thank you, Dr. Ganeshwaran. With a great pleasure, we invite an expertise in engineering, our keynote speaker, Professor Kiruba Sivasubramaniam Haran, from the Department of Electrical and Computer Engineering, University of Illinois, USA. Professor Kiruba Haran is the Granger Endowed Director's Chair in Electric Machinery and Electromechanics in the Department of Electrical and Computer Engineering at the University of Illinois at Urbana-Champaign. Dr. Haran moved to Illinois after spending 13 years at GE Research working on electrical machines for applications ranging from power generation to aviation. At Illinois, his work has focused on high-specific power machines for electrified transportation and renewable energy. Dr. Karan is a fellow of the IEEE and member of the National Academy of Engineering. Today, we are privileged to have him share his insights and expertise in a keynote address. Our warm welcome to Professor Kiruba Sivasubramaniam Heran.
Hello, everyone. Vanakkam. Thanks for having me. Today, I would like to talk to you all about superconducting machines. This is a way that we think we can make electrical machines become lossless. So I'm going to share a presentation and walk you through the talk. Let's see here. All right, so I think everyone is familiar with the electrical machines. We use them anytime you want to convert from electrical to mechanical or mechanical to electrical motors and generators. They are very common as in all kinds of industries, from power generation to industrial to transportation, and they are becoming increasingly more popular as we go through the energy transition, especially transportation as an example. Electric machines are typically lossy in the sense that they are not 100% efficient. If you start with certain amount of mechanical power, by the time you convert to electric, you get less. And the reason is some of the energy is converted to heat through electrical conductors, copper or aluminum. Now, superconducting technology allows us to go to a future where the conductors are lossless. They're superconductors, as the name implies, no ohmic losses. So I want to walk you through, just a quick introduction. I think everybody is familiar with superconductivity and how it could impact electric machine sizing and performance. And then we will go through some of the reasons why superconducting machines don't exist today. And this is because of the challenges related to cooling, AC losses, the ability to handle fault conditions, and so on. So I will highlight a few of these. And then I will pick one or two examples of current technology and what people are working on. I will use an example from our research group here at the University of Illinois and a spin-off company we have here called Hynetics. I know this is an online recording, so we may not have a chance for a Q&A, but I hope people follow up with emails or some other way to connect if you have questions. Okay, so superconductivity. What is it? And again, I think you know this from high school physics. If you take a conductor, say something made of copper, and if you heat it up, the resistivity or the resistance of the conductor or the resistivity of the material actually gets worse. It gets higher with temperature. And the flip side is also true. If you cool it down, then it becomes a better conductor. And that's kind of what you see in the red line here, right? So if you go cool the conductor down, say from room temperature, and you go towards absolute zero, the resistivity gets lower, or conductivity gets higher, and you have the curve seen in red. A superconductor, on the other hand, you reach a temperature called the critical temperature, where the resistivity drops, it vanishes. It basically becomes zero. So the idea is, can we use that superconducting phenomenon, which will be somewhere, below the critical temperature, and take advantage of the lossless behavior? To relate this to, your fundamental electrical engineering, you see here the resistor. You have voltage across a resistor which would drive current. If it's superconducting, that R goes to 0. So Ohm's law, no matter what current you have, the voltage would be 0 across a superconductor because the resistance is 0. What that means also is that the power dissipation, voltage times current in an instantaneous sense, even when you average it over time, um, traditional conductors would have I squared R, ohmic losses, that becomes 0. All right, so that's the benefit. What's the issue with superconductors? Everything that's been discovered so far operate or become superconducting, or say it another way, the critical temperature of most of all of superconductors that have been discovered so far are well below room temperature. You see the plot here on the right. Going back to the discovery of superconductors, the early 1900s, the temperatures were below 10 Kelvin, the critical temperatures. And then over time, people have discovered better materials. In fact, in the 1980s, a new class of superconductors, the cuprates, were discovered that pushed the critical temperature to above 100 Kelvin. Still far below room temperature, but getting to a point where you can build a practical equipment out of that. More recently, here in the top right, this is interesting but not very practical. Under high pressure, you can have some materials that become superconducting at temperature that are now approaching room temperature. But again, not very practical because look at the pressures here, gigapascals, hundreds of gigapascals. Like the pressure, I think it's even maybe higher than the pressure at the center of Earth, or really high. Okay, so if you want to use a superconductor in a practical device, you have to get it down to fairly cold temperatures. That's the takeaway. But people have managed to do that. In fact, there are superconducting power apparatus that have been developed over the last several decades and demonstrated in some cases in real world applications. Electric machine, there have been several. On the top right, you see a wind turbine that actually had a HTS, or high temperature superconducting generator that was used to generate power from the turbine. It was connected to the grid. It ran for several months. So we know it works. Same thing for transformers, fault current limiters, power cables, magnetic energy storage. I mean, here are some figures on the right here about places where even today you have HTS, or superconducting cables, that are used to transmit electric power. Unfortunately, challenges related to the cost of the economics and the complex technology that's involved makes these things more of technology demonstrators rather than practical, commercially viable products. So that remains the opportunity, and that's what several groups out, certainly here in the US and globally, are working on. And we are one such group, and we focus on electric machines, superconducting machines. Why do we care about superconductivity in electric machines? Just a very quick overview of the fundamentals of electric machines. How do machines work? So take a cylindrical radial flux, traditional electric machine. The way it works is use magnetic fields. You will have a component called that the rotor, which is cylindrical. This magnetic field either produced by it or from the stator, and then it interacts with another field. So you have the rotor and stator, and the magnetic fields from both that interact to produce torque. One way to think of that is that there's field from one member and current in the other member. Anytime you have current, there's field, but it's just nice to think of them as, field from the rotor as an example and current in the stator. They interact to produce the Lorentz force. You can further derive an expression for the torque in terms of the flux density and the current density. Right? That's what you see here. B sub r is the radial flux that comes from the rotor. J sub L is the linear current density along the peripheral direction of the motor. So the product of all these terms is the torque. One thing, and then kind of jumps out at you, is the terms here. This 2 pi r, the radius, L is the active length. And the radius occurs twice because one, to integrate the cylinder to get the total shear force. And then you have another radius because the lever arm, if I have a force at a certain radius from the axis of rotation, the torque is a product of the radius times the force. That's why you have the second R here. If you look at this product here, that relates to the volume, pi r squared times length, meaning that the torque per volume is going to be proportional to B sub r and J sub L. It's proportional to flux density times the current density. And this is kind of intuitively obvious. If I can push higher and higher flux densities and higher and higher current densities, the torque per volume or the power density improves. Right? And the second key parameter in electric machines is the efficiency. So the input power minus any losses. Usually you say input power minus losses over the input power would be efficiency. In a superconducting machine, we would say, well, if the losses are not at room temperature, if they're at sub-ambient, then you need to somehow lift that heat to the ambient or even above the ambient to be able to exhaust it to the environment. So there's a coefficient of performance associated with those losses. So this becomes the net efficiency of the machine. So these are the two sets of parameters we care about: losses and flux density and current density. Right? All right. So maybe I should say both of these are much better with a superconductor than conventional conductors. Right? If you're not producing ohmic heating, you can keep pushing higher and higher current density without worrying about additional losses. And if you have higher currents, you can also generate higher magnetic fields. And you can go an order of magnitude higher in flux. So traditional electric machines are maybe a Tesla. You can go all the way up to like 10 Tesla or even higher, in theory at least. In terms of current density, conventional machines run with maybe 10 amps per square millimeter. You can push it a little higher if you have better cooling. But the superconductor can go to hundreds of amps per square millimeter or even 1,000 amps per square millimeter. So that's the benefit. But these machines are very hard to design because, like I said, no room temperature superconductor, so you need to be able to cool them down. There are two major ways to do that, either open loop cooling or closed loop with a cryocooler. We'll quickly look at that. We'll look at this phenomenon called AC losses. We'll touch on that. And then the real reason why these machines are not used widely or there's no commercial application is because of concerns about the reliability of what is still considered exotic new technology, right? And then at the end of the day, everything has to be easy to manufacture and be cost effective. That's always there. I won't talk much about the fourth item. All right. How do you cool the machine down? First way is open loop, which is you get a cold liquid. Let's say liquid helium. If you had liquefied, if you liquefy helium and you carry it around in a bottle, if you pour this over something, it's going to boil, and the boiling point of helium is 4 Kelvin. Now that can be used as it's boiling, it's extracting heat from the device, and you can cool things down to, the helium boiling point type temperature, single digit Kelvin. Another example is hydrogen. Hydrogen boils at 20 Kelvin. It's becoming more popular because of the hydrogen economy. Hydrogen can be an energy carrier, just like you have batteries, and use the hydrogen as fuel. So if that's available, you can use it to cool your device. It boils at 20 Kelvin. So you can have a machine that operates at, say, 30 or 40 Kelvin and use liquid hydrogen as the coolant. Liquid nitrogen is another option. It's more widely available. As you go higher and higher in temperature, it's easy to liquefy them, and they become, that much cheaper as well. So these are temperatures you can get to with those cryogen and literally open loop cooling. You bring a bottle of this cryogen and boil it off. As it's boiling, is cooling the device down. And the solid lines are the critical surface of superconductors. This is in terms of temperature and critical field. There will be a third dimension, that's the critical current density. But even in terms of field, you can see, how high a field you can get to with any of this cryogen that could be used for the cooling. On the right here is, some idea of how much cooling capacity is available. So you see the temperature, but then how much liquid do I need to extract a certain amount of heat? And it goes back to the heat of vaporization as well as the specific heat capacity. Both combined together gives you these numbers. Takeaway is there are ways you can cool this if you have access to cryogen. So one way this is utilized is this aircraft concept called Cheetah. This is a program here in the US. There's a similar program in Europe called Ascend, led by Airbus. The idea here is instead of jet fuel, you use liquid hydrogen as the fuel for the aircraft. And this hydrogen could be generated from renewable energy. So it becomes a green fuel for aircraft and help decarbonize aviation. So you carry the fuel, and then before it's sent over to the fuel cell or wherever else the energy is going to be converted, you can send that liquid through the machines and the transmission cables and maybe even the power electronics and cool it down with that hydrogen. Such an airplane carries a lot of hydrogen. So you see the amount of the several metric tons of hydrogen required for this 8 hours of flight for this particular aircraft concept. So that gives you a lot of hydrogen you can boil off. From that, you can back out how much heat capacity is available, and that becomes your your cooling budget, right? How much heat can you extract from your motor? So you can now take that and go and design a machine to suit this application. So that's one example. But you may not always have the luxury of free cooling from the fuel. What if there is no hydrogen available? What if it's a regular aircraft or an industrial application or a wind turbine? So there's no coolant available. Then what you have to do is put a refrigerator, right? Some way to cool the machine down. What that really means is you have this kind of like a heat pump, if you will, to take the losses that are produced at the cold temperature and lift it up to a temperature where it can be dumped into the outside environment, right? So you had to take it slightly above the ambient temperature. Now there is fundamental physics, Carnot, established kind of the ideal cycle because you're doing work really, to push that heat up. And this curve here on the right is kind of the ideal coefficient of performance. How many watts? This is in terms of efficiency, but another way to think about it is how much energy you need to move to lift up a given amount of energy at the low temperature. This is saying as you approach 1%, that means you need 100 times more energy to lift 1 watt of heat. Let me say another way. You need 100 watts of energy to lift 1 watt of heat from, I don't know, a few Kelvin up to room temperature, right? You see that the coefficient of performance improves as you go higher and higher because it's less difficult as the temperature difference gets lower and lower. So that's theoretical limit. The figure on the left shows you a set of practical coolers. I mean, these are things you can buy, and the coefficient of performance. So let me try that example again. So get to say, I don't know, 4 Kelvin or so, to lift 1 watt, you would need, this is a practical cooler now, you need several thousands of watts. You may need 5 kilowatts to lift 1 watt of heat. So it's hard to imagine you can build very efficient electric machines at those temperatures. But now let's jump to say 50 Kelvin. Now to lift 1 watt, I need something like 15 watts. Still not that efficient, but much better than down at this single digit Kelvin. But keep that in mind. And then if you care about size and weight, this shows you the practical coolers, the mass of those coolers. You may want to pay attention to that as well. Okay, so what do we do with this information? Well, I have to now couple this with the amount of heat I would generate in the electric machine. And you may wonder, hey, this guy comes in and says superconductors are, perfect, no losses, and then he keeps talking about heat that needs to be lifted. What's the deal? Well, the issue is electric machines have alternating or time-varying currents and fields. Superconductors are lossless if you have a steady current or you place it in a steady field. But once you start changing either of those, then what you end up doing is you're magnetizing and demagnetizing the superconductor. It's not unlike the hysteresis that you see in ferromagnetics. Each time you go through a cycle of magnetization and demagnetization, there's losses associated with that. Right? It's not a perfectly reversible curve. So that's the first loss mechanism you see here. And then you have other loss mechanisms because these superconductors are, especially the HTS, high temperature superconductors, they are usually inside a metal matrix or deposited on a metal substrate. Even lower temperature superconductors have a lot of other metals that are used to construct the cable or the wire. So you will have eddy current losses associated with that. And then to minimize the magnetization losses, we make the superconductor out of thinner, finer strands, like you see in the top right figure here. So this is a single wire, which is less than a millimeter in diameter. But you see the superconductors are all those black areas here, many small strands. This helps to reduce this magnetization losses. But if they're embedded inside a metal matrix, then you could have these strands couple with each other. So that's another loss mechanism, coupling. And then transport current losses, this complicated formula, but you have expressions for all of these ways of producing heat. So you actually have to go and compute how much losses you have in an electric machine, even though it's superconducting. How large are these losses? Well, here are two examples. One is for a machine that's designed for fairly high speed. That means it runs at high frequency. Another lower frequency, low speed, a wind direct drive machine. The left column is a smaller machine, 2.5 megawatts. And in fact, in terms of torque, is even much smaller. This particular machine is designed to be very high efficiency, 99.9%. The wind machine, also high efficiency. In fact, it's a little higher efficiency. And the reason is because of the frequency dependence of the AC losses. Look at these two cases here. The loss as a function of flux density at 1.3 hertz, and similar curves for 300 hertz. So this is like a high-speed machine, industrial, aerospace, and this top here would be like a wind generator or a ship propulsion motor. They could be fairly low frequencies. Note the scale. The loss density at 300 hertz is hundreds or maybe even 1,000 times larger than what you see at the lower frequency. So that's why you see the difference in efficiency. But this efficiency does not include the cooling power required to maintain the temperature at the cryogenic temperatures. So now you go and take the coefficient of performance we just saw earlier. Even though the losses are only 0.1%, by the time you apply the amount of energy needed to lift that heat and get it out of the machine, the net efficiency drops to 95%. And you look at the mass of that cooler, it's vastly much larger than the rest of the electric machine. So it makes the closed loop cooling system not very practical for these high-speed machines. For the low-speed machines, you see that you end up with 99.5% efficiency net, and the weight is not that much higher than the machine weight. 17,000 kilogram for a 10 megawatt, 10 RPM machine is still much lighter and smaller than conventional technology. So that's the first takeaway, I hope. In the presence of AC losses, low frequency machines are practical. You can put a refrigeration system and make it very efficient and lightweight. High speed machines are more challenging to do closed loop cooling. So what does that mean? Does it mean we don't do high speed machines with superconductors? No. What we do is we take an intermediate step called a partially superconducting machine. So what was the issue with the high speed? It was the AC losses. Anytime you have time varying fields and currents, you have a lot of losses. So what we do is we go find the part of the machine where you have steady currents and steady fields. So as an example, in a synchronous machine, which some of you may be familiar with, the rotor is typically a constant current DC field excitation source. So in that machine, what you could do is make that part superconducting, the field winding, and the part where you have the AC power, the armature or the stator, you could keep conventional, copper or aluminum. Now that's a partially superconducting machine. Now it's truly lossless because it's DC and constant field. And it turns out even such a machine could be very attractive in terms of power density and efficiency. So that's where most of the focus is today in terms of practical machines for a wide range of speeds. You may want to look at a partially superconducting architecture. But you're not completely out of the woods. You don't have ohmic losses, no I squared R because there's no R. But then, since you're maintaining the superconducting coil at cold temperatures, then you could soak in heat from the outside. These coils are going to be assembled onto the rotor. The rotor is producing torque and is driving a load, and that load will be at ambient temperatures. So you have to be careful about how to mechanically connect this superconducting cryogenic rotor to an ambient shaft without heat soaking back in. There could be convection, there could be radiation, and you may need to power this winding. So there are other loss mechanisms. We call this parasitic heat, right? Not the traditional large amount of heat from I squared R, but all these other mechanisms that could introduce some heat. And you need to get this out of the cryogenic environment for the superconductor to remain superconducting. Right? So this is where the practical engineering comes in. It's a very multidisciplinary engineering. So the electrical engineers are working with, closely with the mechanical engineers and so on. Keeping an eye on the time here, I think I prepared a lot more material than I could cover in about 30 minutes. What I'll do is flip quickly through the rest of the charts. I mentioned for practical application, you have to pay attention to failure modes. That's another area of active research. I won't dwell on this, but this is concept of quench, which is like an Achilles heel for superconductors. Anytime there's a small disturbance, the superconductor could become normal, no longer superconducting, and all the stored magnetic energy in the system could, very quickly be dumped in a very small area and could be very damaging. But there are new solutions to this problem called no insulation coils. So it's a passive way to handle this. You see some example coils. Our group here has made coils here, no insulation coils in the Hynetics. Some of you may have heard about Commonwealth fusion or fusion plasma containment. They again use this large superconducting coils, and they use similar, generally the same technique to protect their coils as well. So that's becoming widely adopted. You have to pay attention to system dynamics. I will not go into this, but superconducting machines work differently in a system. You have to pay attention to that. And maybe I will spend a few minutes on this, even if I run over time. These machines they can be very efficient, but we also need to maintain similar levels of reliability as, very simple industrial motors out there, like an induction machine, very simple rotor. You have like an aluminum cage, steel rotor, no need to connect anything to it. It can run for years without any maintenance. But now you put superconducting coils, they need to be cooled. Somehow you have to send some type of a coolant into it, extract the heat, and send to the ambient. So this is kind of a schematic of how such a thing could work. One of the biggest challenges is any kind of refrigeration that system you have would be stationary. So you would need to get, if you have a coolant, as one way to cool it, you'll have to get it into the rotor through a rotating coupling. That can be a reliability concern. And you may need to, pump the fluid in and out. So many parts, so many opportunities for failure. So one way that's being addressed is with an onboard cooling system. So have the rotor have an integrated either Stirling cycle or typically Stirling, a compact cryocooler, which would keep the rotor cool without cryogen coming in and out, right? We call it cryogen-free electric machines. Several groups are working on this. That leads me to the example I want to cover. So this is a cryogen-free machine that we are working at Illinois. along with the company called Hynetics. It has all the features I just talked about, partially superconducting, no insulation HTS coils, and the cryogen-free cooling system with an onboard cooler. There are a lot of details that need to be worked out to make it practical and reliable. I'll just run through the slides here on how the team has done a lot of bench testing, subsystem tests to retire the key risks. And they are proceeding to now put the whole motor together. And I think this is the money chart here. This is kind of showing now the risks are retired. Let's put the machine together, pick an application. One of the first we are doing is for aircraft propulsion. And you compare this machine to others that are out there in terms of two key metrics, power, specific power and efficiency. These machines are up here, the green and the red. Conventional machines are down here. So you see how much better these machines can get with superconducting technology. I think this last slide here is just to say there are several groups around the world that are working on this for both aircraft as well as wind turbines, as you see on the right, ship propulsion, industrial, you name it. So there's kind of a race going on to see who can come up with a, practical machine, and we are happy to be, or I would say we are excited to be in the race. Some takeaways, but I'll wrap up the talk. And like I said, happy to take questions, comments offline. I think I'll share my email address with the appropriate people at the conference so we can connect. Thank you all. Thanks for having me. Good luck with the rest of the conference.
Thank you, Professor, for your valuable insights. We are honored to have with us Professor S. Sri Satguraraja, the Vice Chancellor of University of Jaffna and the General Chair of ICE 2024. We cordially invite Professor S. C. Satguraraja to deliver his insights as General Chair of ICE 2024.
திருச்சிற்றம்பலம் கலைகளெல்லாம் அருளும் கலாவதி உம்மை காத்தருள்வாய் அன்னே சரஸ்வதி அலகிடல் சூழும் இந்த உலகினிலே உனது அருளின்றி செயலேது ஆதாரம் நீ கலைகளெல்லாம் அருளும் கலாவதி உம்மை காத்தருள்வாய் அன்னே சரஸ்வதி. So I paid my respectful obeisance to the goddess of learning. So we created a lady. Her celebrations is coming in the September month, the third starting, Navaratri. So we have a 3-day celebration for Goddess of Learning, Goddess of Learning. So in our emblem, University of Jaffna, you can see 64 flames. These flames notes 64 arts. That is in our wisdom, the Vedic culture. 64 கலைகள், ஆய கலைகள் 64. So that is the university. Engineering is art of providing comfort to the human beings. So enhance our quality of life in all aspects of domains. from superconductivity machine for transport, energy transformation from renewable energy to their wings and motors, to the health sectors, now the biomechanics coming in, and then the agriculture, the IoT, smart agriculture coming in, even the combined harvesters are operating in the paddy field everywhere in the world, even the third world now. The human labor is now redundant. So all transformations are happening. But human beings, according to the ancient knowledge from Agastya time, they exist millions of years. Even Rama Janmabhoomi now celebrated the Ayodhya, the big temple inauguration. Rama lived 1,000 years in the Treta Yuga, that million years old. The Kali Yuga has started. According to timeline, I'll tell you, there are evidence. We have a discipline called archaeology in the University of Jaffna. So now the more and more evidence are coming. So in the Thuabara, if you go to Vrindavan, you see the Krishna's evidence. So before Treta Yuga, they use all the weapons. Even there is a weapon called cold weapons. Now scientists are thinking superconductivity. Cold weapons. So when you fire it, everything gets frozen. So you can recover all the assets. Now at the moment, Shiva's weapon, Pasuka, all are fiery weapons, so all burn everything. So now we are trying. As a human beings, we have our own endeavors. So we can't rely on angels and wisdom from the other sources. So human being, we always trying to get our knowledge from ascending fashion. From the childhood, even myself, I accumulated knowledge from the ascending fashion. So I started something like, mummy telling something, hearing. So I start from hearing. I never start from writing, not referring notes. So it started from hearing. Then knowing. Then I start reading. Then, of course, realizing. I did my PhD in 1987. I know German scientist Alex Muller got a Nobel Prize for superconductivity. At the time, my home was displaced with the Operation Liberation, first war attack in the homeland of Tamils, 1987. IPK came with that attack. So I'm telling the timeline. So 1987 only the superconductivity became feasible because someone found superconductor material with the reasonable temperature. Today, after 1987 only Google came, by the way. Now the Google is a household thing. I don't think anyone live with the Google. Even the children now play with the Google. So now, after 40 years, now a person, Subramaniam, you know Subramaniam. We always sing Subramaniam, Subramaniam. So our Subramaniam is a deity we assign with the Tamils. Muruga. So Subramanian Haran today is speaking about the possibility of having a cheetah from the NASA that may operate with the no loss situation. Even Atpuraya got a grant from, I don't know, Erasmus or some grant, zero emission. I was in a Kalahari hotel listening to the zero emission business. So now people are targeting zero emission. These are all happened in 100 years. 1911 only superconductivity was first spoken by a Dutch scientist. I checked in the Google anyway after listening to this talk. 1911 only our doctors found blood groups. The transfusion, blood bank came in after 1911, 1921. The man-to-man transfusion done without knowing even the blood groups. So just imagine last 100 years, lot of celebration. Now the conference is a household thing everywhere because explosion of knowledge. We say exponential. So knowledge doubling taking place, the time required is halving. That is called the exponential, you know, the radiation business. So this environment, now our university is 10 years old. Ganeswaran leading the faculty is the third dean. The second dean is first dean, no, yeah, the first dean, Atporaya, is coming, is IESL's chapter. And also is a present vice chancellor of the University of Vavuniya. So a lot of changes are happening. We are growing, but at the same time we are facing a lot of challenges. The Jews began in 2012 under very trying circumstances. Soon after the recommencement of activities, and our university is integrating the mainstream of activities after the Mullivakal come down in 2009-10. Before that, we were cut off from the mainstream of activities, but the university was progressing. Now, I am proud to say our university is one of the largest universities in the country, with the 12 faculties, from indigenous medicine, Siddha, to the Western medicine, from engineering to technology. So we are expanding. So this conference is another second conference. So where everything shared to the international community. So now the live stream coming. So it's a wonderful atmosphere, and also is pave the way for the youngsters to, you know, give their thoughts, not just in the room, it's now going into global. Because innovation happens just from one idea. One simple idea, things may change, entire world. Einstein thought of something, still people don't know why did he think like that. He thought we came with the lighting of the oil lamp. He said the velocity of the light is independent of source and observer. Still people wondering. Then he said the limitation for the signal processing. That is 3 into 10 to the power 8 meters second square. You cannot go beyond that. That's a theory of relativity. That is quantum mechanics even failed to explain. Only the gravity explained by the relativity theory. Still the postulates are open for verification. So someone thought, but that man was running for his life from Germany, not in a comfortable place. I don't think 1940s, 50s a very comfortable place for a Jew. So ideas came. Still we were wondering. Then the nuclear revolution came, because E is equal to mc squared came. So now we know I carry a lot of energy in my existence. Because agriculture faculty, we had a theme seminar, and also our keynote speaker was talking about agribusiness. So agribusiness, they are thinking about, you know, post-harvest preservation, packing. The engineers could come in, because 1/3 of the food go waste after production. In Jaffna, that's the situation. We have excess production, but the only thing is value addition needed to make them, you know, profitable. So that's what we are 3 faculties together: engineering, agriculture, technology. When you join together, we are individuals. You know, by nature, our fingerprint is unique. I have my purpose of life, right? I have my family, I have my relatives, I have my, you know, ethnic group, my homeland. On top of it, I had to join with other people to punch, to remove challenges, encounter challenges. So if you go to, if you trace back the conference culture, when did first started? I don't know, this Madurai, our people say, Changam Valatha, Tamil Valatha. Madura Changam. If the Madura Changam is not there, there is no Tamil language preservation now. If you go beginning of the Kali Yuga, 5,000 years ago, in a Naimiswarian forest, they were discussing about encountering the Kali Yuga, because hypocrisy. The age of hypocrisy. Even Jesus came and talked about this and killed. Martin Luther King was killed. Mahatma Gandhi was killed. Right? Because they were talking about the fairness to the people. So age of hypocrisy, they were trying to meet and encounter this. So in the timeline, we are progressing. We are the human beings, the only being. I tell you engineering, I was taught how to start my talk. So engineering engine. Okay, in Tamil also nicely said. Yandram, Yandri. Indri. Huh? Okay, what is the best engine you ever come up with? Okay, superconductivity or whatever the best engine, zero emission engine. Okay, no fuel, take a hydrogen from the air and convert it and do everything. What is the best engine? This is the best engine. It's a gift. It came from my parents' mating. Right? Then it's growing. Then it's dwelling. Then it's vanishing. But it's performing. Consuming the air. And the dance happening. Heart pumping. Now Ganesharan talk about, Thiruvaran talk about IoT. The best IoT is here. Action is there. Sensors are getting the input. The processing done. So all these done there. So it's design, it's a gift. It's not by accident. It's not by accident because you are enjoying your life. So our existence is there to enjoy the Ananda. Anandamaya and Arivai. So we want to be happy. Happy, there is a word. I always say one song, Anandamaya and Arivai. Knowledge bring happiness. Clarity bring happiness. Not by doing rituals. Rituals bring, like our Taliban, some madness, fanatic. You know, they do a lot of things, then hard things than us, some of the ritual followers. But they are fanatics, they kill other people for no reason. So clarity brings happiness. That's what university is built, not very old. Even the oldest universities, in the modern universities, Oxford, Cambridge, Paris, only 900 years old. So our university in the golden year. But we are aspiring for our engineering faculty many, many years. It's only last couple of months ago we celebrated the decade of existence, 10 years of existence of engineering faculty. Now it's expanded. The input is more than 200 people coming from all over the country. So this is a knowledge churning place. When the people churn, things come. Otherwise the milk get fault. If you churn, the butter come. Butter lasts, even in the water. Milk won't last. The churning happened. They say the Devas were churning, Lakshmi came, wealth come. Lot of startup come. Illinois man is running a startup. I know in the science faculty conference, there's somebody called Sabeshan came from Cambridge, engineer, electric engineer, batched up in Sri Lanka, went to Cambridge for first degree. Now he startup, microwave communication, and his startup, he has now this, sensors, IoT thing in the supermarket everywhere. He pick up people, in the nature of affection and kind of things. It's very modern. It's a multi-million business now. A guy from our village, your village, right? Mayuran village. So these things are happening. So spin-off companies are now is in the agenda because our undergraduate training education gets saturated. Now engineering is done everywhere. Silit come, even Kandarmadan Junction, somebody come. Tamana came and mobilizing people for doing the engineering. Some idiots are doing this. Even now some youngsters are asking whether weekend I go and teach there. I say no. I got a letter even a couple of days ago in my month. I am not going to allow. You go, better go there. You join with them. Because now everything getting diluted. That is IESL very important, you maintain the standard. I think that is a very important business. Otherwise, engineering sector come. Doctors also now getting diluted. Anurag come, maybe he will stop this. Because JVP is not going to allow doctors being inflated. So a lot of challenge coming. A lot of fake things are coming. Fake publication I have encountered at Puraya knows. Even academies are getting polluted. Because in the third world, anything happen. We want to be great like any people, no time. So there are a lot of challenges, but engineering, timeline, expanding. Now the super highway is open. So before 2000, this phone is not there. Now everything is done. We are in a blessed nature. Online teachers are coming. Subramanian Haran is coming. And they are prepared to conduct lectures for us. Our time, these facilities are not there. But still the indigenous people are good. Because they enjoy their life. Because I tell you, Valgama, the engineer, I was talking about our engineering Peridinian people. We are hard in mathematics. So even Subramanian Chandrasekhar, another Subramanian Chandrasekhar got a Nobel Prize from Chicago about the critical mass of the black holes while I was doing the PhD. He never went to any lab. He said never used even a microscope. Hawkins is a crippled man, found everything, working on the papers. Same thing with Einstein. So the best mathematical brains come from this part of the world. That's what they do well. Our Professor Alagaya Turraya portrait we opened. Alagaya Turraya was the best mathematics student in the A level. He was a gifted student because of family circumstances he went for engineering. Then his disciples are decorating the California. Disciples in the geotech. Many. So I think while we are inaugurating our Faculty of Engineering, many scientists from all over the world, helping us to get the best curriculum and also give exposure to our people and hosting them in US universities. So this entire world is a globalized village now. So wonderful opportunities. Ladies and gentlemen, juice provide the thing. The juice I always say, I say coconut, the lemonade part, deceive, protect from choking. Then that is our skin. Because there are so many microbes who want to attack us. Our skin prevent this. Then there is a fiber part in the coconut. So that is our 72,000 nerve system, air floating. So here also that floating, because that keep our balance going. If our ears got balance not maintained, then we get confusion. So then skull, top computer is there. Then the kernel. The kernel is the intellectual part. I'll finish it off. The kernel, the coconut scrapple thing, we put in the physical existence, the coconut milk. Then the juice, that is a super thing. My medical friend said, when the LTT was in trouble in the jungles with the fight bleeding, they don't have access to this kind of infusing, this saline business. So say they simply cut the coconut and infuse. Because coconut composition and the blood composition are same. Readily accepted. That's what we Tembli in the hospital when you have trouble, because it's nicely accepted. Similarly, the Jews give you the best of best thing from the researchers to disseminate. I welcome the people from India coming and doing the presentation. You are not only nearest neighbor, people are swimming the parks right now. So I will be there in the evening. And the flights are coming, connectivity is coming. The G3 country, G7, it will be G3. Wonderful partner. So thank you very much, ladies and gentlemen. I finished the last thing. Sat Sit Anandam. You want Anandam. Anybody in the world, not for the engineers are doing, sacrificing their time. Give best things to the people. Anandam. How do they give? Sat Sit Anandam. Sat means the noble quality. Now engineering education, we teach humanities. We teach ethical thing. Because non-ethical things are coming up. So Sat means gentleness. I know some people are quarreling for no reason. They are putting lot of trouble to the people. So harmony, Sat. Siddh, that's the knowledge. Siddhas. They know things as it is. So that is the power of knowledge. Just to capture the fundamental rule governing. Newton captured the lower gravity. So we know Earth goes around the sun. angular momentum is preserved because of central force motion. What is angular momentum? Millions of kilograms of weight, millions of distance from the sun, then the weight, distance, and the velocity. The velocity is 107,000 kilometers per hour. This mass is rotating. Angular momentum is given. Angular momentum is given. So like our satellite putting in orbit, these are mass things have been arranged for us to enjoy the life. Capturing those things, we did mathematician, preservation of angular momentum, quantum mechanics, statistical mechanics, right? All kind of celestial mechanics, continuum mechanics. The science faculty give this as a gift to the engineers to use it. Now I know the civil engineering head, K. Reason, now doing the microbes to let the concrete, these cracks to be fixed. So microbes, even biomechanics, all are coming. So human things in mechanics, but the nature thing in non-mechanistic, I don't know, heart pumping, what mechanics is that? No motor, no energy coming from my, I ate some green grams, so coming from green gram, no hydrogen, no superconductivity, nothing. So these are happening. Thank you very much. There's a lot of thoughts coming in, but wonderful. I congratulate the new dean. So Atparaja, Prabha, Ganesh, and the young people, Janathanan and Thiruvaran and the team. I know a few people are here now. Don't worry. Few people made the change in the world. I know you are sacrificial lamb. The Jesus sacrificed his life for the betterment of human beings. Now he is celebrated. AD and BC. Similarly, so many people. Don't worry about people are not there. Time will bring. Now the political changes are happening in Sri Lanka. No, the time brought it, no. They were rebels 30, 40 years ago. So similarly, people will come. Anyway, I am so excited about our engineering faculty, one of the best faculties in this part of the world. IESL people are here. Thank you very much. You contribute a lot and you are assistant in various things. And I remember Turraja, Mahalingam, wherever I go south, I tell I am coming from their village, they salute me. Even Abhayakon, now governor, vice chancellor, when I say Abhayakon, I am a next door neighbors to Turraja, come on, they respect me. So such a wonderful reputation they created. Now Sudha is doing well in the irrigation. Anyway, thank you very much, ladies and gentlemen. I am so emotional. Thank you.
Thank you, Professor, for your enlightenment in science and development in multidisciplinary domain throughout the history. Your knowledge brought us happiness. It's a great honor and admiration to have Professor A. Atputaraja, the chairman of the IESL Vadakin chapter and the vice chancellor of the University of Vavuniya. We warmly welcome Professor Atputaraja to chair the stage.
Good morning to all of you. Our Vice Chancellor, Professor Sri Satkunaraja, Dean Engineering, Dr. Kaneshwaran, Professor Thiruvaran, and Dr. Janathanan, all my colleagues, head table members, head of the departments, and our IESL council members, 3 council members are here, and my colleagues from Engineering, IESL Vadakin chapter, plus all other visitors. It's a great pleasure to be here in the second international conference in engineering, which are basically worked out by Dr. Janathanan from Faculty of Engineering and Mr. Kajivan from IESL Vadakin chapter, with the leadership of Dean Engineering Dr. Kaneshwaran and Professor Sri Satkunaraja as a Vice Chancellor. It's a good that development here I can see compared to first conference to second conference is solidly collaborate with IESL Vadakin chapter. It's link up these engineers and the academic researchers together as a conference where a lot of research dissemination is going to be presented. And the new government, as our Vice Chancellor said, is going towards more and more efficient and effective management, loss-free, ULL-free, everything is free from bad side and going towards good side. So where they are giving higher priority for entrepreneurship, research and development, and startup business, and going towards more contribution or direct contribution to the country economy. And also, this conference, whenever we see from the engineering solutions, a lot of engineers are here. They have, again, they have initiated engineering forum, so many places where real world problems are being discussed among engineers, and it will be, I hope in the future, more and more closer relationship with the universities will bring the engineers all the problems to the universities and get through the research and development and find the more sustainable solution for their real world solution to the real world problems. I will just brief one item. Recently, even Eastern University also take it forward to establishing the Techno Park, where the real industry link up with the university and find more and more sustainable solution for their problem. All the universities are going in that direction, Jaffna plus Vavuniya as well. Just a simple example, we learn amplifier in our A-level or in O-level. Transistor, diodes, logic gates, then finally come to amplifier. That's what I did recently, the A-level practicals to the students. So from that, when we, as an electrical engineer I am from, when we come to the university, we are learning amplifiers in depth. Today, all of you have amplifier in your hand, which is mobile, which is amplifying this microwave with the battery power to the reasonable voice where you can hear and talk. So it, as Vice Chancellor said, engineers make very conducive life for the people. This mobile has brought you very conducive, very easy life for you. You can talk anywhere you are from and things like that. So much of easiness in our life coming from this finding technologies. These are starting from very basic, very simple basic, and finally come to some technology development, which make people life much easy. This is where the real world engineers and the researchers need to collaborate very strongly. We can find so many solutions. When we find solution, now you can see every mobile is sometimes starting from 2,000 to 3 lakhs rupees. A multi-million dollar business is generate money inside the country. So why don't we continue this collaboration more and more strongly in the future and find more and more dissemination of knowledge to solve real world problem, make people life much easy, make the business running very fast, and get more and more multi-million dollar business coming directly from as the outcome of the research and development. So I am very pleased to the gentlemen, ladies, who has worked very hard for this conference, taking these engineers very solidly collaborating with this research environment in the university life. And also, you can see Professor Krivakaran is telling about loss-free, superconductors, more efficient, effective system coming up. So always we had to go in that direction. That is from University of Illinois, one of the top university in US. Similar way, we can bring more and more very effective and efficient management system while solving the real world problem in a sustainable way through this research collaboration. Thank you so much.
Thank you, Professor, for your valuable enlightenment. Now, it's time for one of the key highlights of our conference, the release of the conference proceedings. These proceedings capture the essence of the research presented at ICE 2024, a testament to the hard work and intellectual rigor of our researchers. I invite the dignitaries on stage to officially release the conference proceeding. We cordially invite the editor, Professor T. Thiruvaran, to present the first copy of the conference to our Vice Chancellor, Professor S. Sri Satguna Raja, to officially release the conference proceeding. With great pleasure, I invite both the dignitaries.
Thank you. Next, we kindly invite Dr. Kaneshwaran Dean Engineering, to present the conference proceedings to Professor A. Adputaraja, Chairman, ISL Vadakin Chapter. Thank you. We kindly invite Dr. Janathanan to present the conference proceedings and mementos to the representatives of our generous sponsors. At this moment, we appreciate the great support we got from our co-sponsor, Salex Renewable Private Limited. We invite our silver sponsors, Asian Paint representative, Mr. Vidyasagar, to accept our proceedings and mementos.
More than 70% of the Earth's surface is covered with water. But we know more about outer space than what lies at the bottom of the oceans. Beneath its surface, the water cradles an active, fragile ecosystem that we
Thank you. Next, we invite another silver sponsor, KUS Scaffolding and Concreting representative, Engineer B. Janagan, to accept our proceedings and mementos. Thank you.
Thank you all. As we near the conclusion of the formal session, it's my privilege to invite Dr. Janathanan, the convener of ICE 2024, to deliver the vote of thanks.
Good morning, ladies and gentlemen. Today, the Faculty of Engineering is conducting its second conference successfully with the collaboration of IESL Vadakin chapter. I believe the collaboration will boost the development of this region. So as a convener, first I would like to express my gratitude to everyone who have contributed to the success of this conference. First, I would like to express my deepest gratitude to our Vice Chancellor, Professor S. Sri Sakunalaja, who is always very supportive to organize this conference. So next, I would like to thank our Dean for this support through this organization. Next, I like to sincerely thank Professor Adputaraja, IESL Vadakin Chapter Chairman, and also the Vice Chancellor of Vaunia, and also the IESL Executive Committee for their support for this conference. Next, I would like to thank our faculty deans, other faculty deans, the academic staff members from the other faculties, also our academic staff, then heads of the engineering from different institutions, then also my fellow engineers who attend this today's conference. Also, I would like to express my gratitude to our keynote speakers, Professor Kirabaharan, Professor Ilakneshwaran, and Dr. Sridharan for sharing their knowledge, valuable insights and ideas. Also, I would like to thank our sponsors because without their support, we can't do this conference. So I like to thank all three sponsors. Also, finally, I would like to thank our committee, the conference organizing committee members, the fellow staff members, the non-academic staff, and also my dear students who supported throughout this particular organizing this conference. Thank you very much.
Thank you, Dr. Janathanan. With this, we conclude our inauguration and reach a pleasant interlude in our conference. It is our pleasure to invite you all to have a tea break. Please join us in the designated areas for refreshment and take this time to visit and have a look at the selected posters of our research carried out by our students exhibited in call number 2. And please use this time to connect with fellow participants, exchange ideas, and enjoy a moment of relaxation.
After the tea break, the technical sessions will be commenced by 10:30. And there will be it will be divided into 3 technical sessions. Technical session 1, 2, and 3, which will run in parallel. Each session will showcase a series of presentation and discussion on cutting-edge researches and innovations and solutions in the field of engineering. Technical session 1 is related to civil engineering, especially related to the transportation and geotechnical aspects, which will be held in hall number 1. Technical session 2 is related to environmental engineering, especially related to water and wastewater aspects, which will be held in hall number 2. And technical session 3 is related to electrical and electronic engineering along with computer engineering, which will be held in hall number 3. We will reconvene shortly to continue with the remaining session of our conference. Thank you all for your attention and participation.